Chapter 3, Vectors and Motion in Two Dimensions. Section 3.4, Motion on a Ramp. A crate slides down a frictionless, that is smooth, ramp tilted at an angle theta. The crate is constrained to accelerate parallel to the surface. Both the acceleration and velocity vectors are parallel to the ramp. The motion diagram shows the motion and the acceleration of the box. We choose the coordinate systems to have the x-axis along the ramp and the y-axis perpendicular. All motion will be along the x-axis. The acceleration parallel to the ramp is a component of the free fall acceleration the object would have if the ramp vanished. The x component of the acceleration down the ramp is plus or minus the acceleration of gravity, g, times the sine of the tilt of the ramp. The correct sign depends on the direction in which the ramp is tilted. The acceleration in the figure is plus g times the sine of theta, but upcoming examples will show situations in which the acceleration is minus g times the sine of theta. A ball rolls up the ramp, then back down. Which is the correct acceleration graph? The answer is D. The acceleration is constant. Since the ball is moving up the ramp, the direction of motion is positive. Since the ball is slowing down, the direction of the acceleration must be oppositely directed, or negative. The Willamette Pass ski area in Oregon was the site of the 1993 U.S. National Speed Skiing Competition. The skiers started from rest and then accelerated down a stretch of the mountain within a reasonably constant slope, aiming for the highest possible speed at the end of this run. During this acceleration phase, the skiers traveled 360 meters while dropping a vertical distance of 170 meters. What is the fastest speed a skier could achieve at the end of this run? We begin with the visual overview in the figure. The motion diagram shows the acceleration of the skier, and the pictorial representation gives an overview of the problem, including the dimensions of the slope. As before, we put the x-axis along the slope. The fastest possible run would be one without any friction or air resistance, meaning the acceleration down the slope is given by equation 3.20. The acceleration is in the positive x direction, so we use the positive sign. What is the angle in equation 3.20? The figure on the previous slide shows that the 360 meter long slope is the hypotenuse of a triangle of height 170 meters. So we use trigonometry to find the sine of theta is the opposite side, 170 meters, divided by the hypotenuse, 360 meters, which gives an angle of 28 degrees. Equation 3.20 then gives that a sub x is plus g times the sine of theta, or 9.8 meters per second squared times the sine of 28 degrees, which equals 4.6 meters per second squared. The acceleration is positive since we define the positive direction down the slope. The skier is accelerating down the slope, so we must be accelerating in the same positive direction. For linear motion with constant acceleration, we can use the third of the kinematic equation in synthesis 2.1. V sub x final squared equals V sub x initial squared plus 2 times the acceleration in the x direction times the distance traveled. The initial velocity is 0. The final velocity is 58 meters per second. This is the fastest that any skier could hope to be moving at the end of the run. Any friction or air resistance would decrease this speed. The final speed we calculated is 58 meters per second, which is about 130 miles per hour. Reasonable because we expect a high speed for this sport. In the competition noted, the actual winning speed was 111 miles per hour, not much slower than the result we calculated. Obviously, efforts to minimize friction and air resistance are working. A new ski area has opened that emphasizes the extreme nature of the skiing possible on its slopes. Suppose an ad intones, "Free fall skydiving is the greatest rush you can experience, but we'll take you as close as you can get on land. When you tip your skis down the slope of our steepest runs, you can accelerate at up to 75% of the acceleration you'd experience in free fall." What angle slope could give such an acceleration? The answer is the acceleration is 0.75 times 9.8, or 7.4 meters per second squared. This means the downhill component of the acceleration is 7.4 meters per second squared. One can also simply say that the component is 0.75 times g, which means the sine of theta is equal to 0.75, where theta is the angle of the slope above the horizontal. For 0.75, this gives theta as 49 degrees.